Alright, hell yeah. So we have physics, and guess what? We got a red problem. You know what I mean? This is most difficult, but check it out. There's no acceleration. You know what I mean? We basically just have a river, and oh man, hopefully one of these pens works. Okay, so we have a river, and I'm gonna say this is, downstream, and it's going with a velocity of 2.5 meters per second. And the length of this is 80 meters, bank to bank. And you're able to swim 1.5 meters. I guess you're delivering a package, who cares, you know what I mean? But now it's just as how much you can swim, you know what I mean? If you're just swimming straight across, that'd be the smart thing to do. You could swim at 1.5 meters per second. How long is it going to take you to get across? I mean, this is just real easy. You can be like, but, don't you just multiply those two together? 1.5 times 80? Well, nah, you don't multiply, but you do have a relationship. So always do the units. This is in meters per second. Cool. And then just do the other one over here. And then what do I want to? I want to find the time it takes to get across. Well, seconds is downstairs. You know what I mean? So I can't just multiply these, because then I'd get meter. You know what I mean? So I must have to divide by meters per second. And meters cancel and seconds goes to upstairs. So I'm going to take 80 divided by 1.5. Cool. 80 divided by 1.5. So just like that, I'm going to store that as alpha t. We have a t of 53.3 seconds. And I'm going to call this theta is equal to 0, just straight across. You know what I mean? Because we're going to vary the problem in a second. We're going to say, hey, maybe we want some sort of angle. And we're going to go 1.5 at an angle. But because now it says, well, it says choose the minimum time you spend in the water, or what direction should you head? Well, obviously just straight across. For this problem being red star, that is the most obvious thing that you can come up with. You know what I mean? Because this velocity of this river ain't helping you get across. You know what I mean? And so then B, it says how far downstream would you be carried? Well, you're going to be in the water for 53.3 seconds going straight across with no downstream or upstream velocity. So you're going to go, so then now you have something again. You have you have meters per second, and then you have a time component. Cool, look at that. Just the units are the equation. Now we get to multiply those together. So we're going to, and then we'll get the meters downstream. So we're going to go 2.5 times that alpha t of 53, and we get distance downstream of 133.3 meters. All right, now it says if you choose to minimize the distance downstream, in what direction should you head? Now just pick a direction, you know what I mean? So I'm just going to pick 45 degrees, and I literally thought that was the answer. I was stumped that it wasn't. But I think what happens, you know what I mean? And this makes sense. I haven't really thought about this one, but it makes sense. It is 45 if you're swimming at 1.5 meters per second and the river's at 1.5. That's what I'm going to assume my guess is. But the river is flowing faster, so there is a sweet spot there. But anyway, let's try theta 45. So that means if you have this 45 degree angle and your velocity is 1.5 meters per second, you have a component in the x direction and then a component in the y. So this is and this is your theta. This is 1.5 sine theta, and then this is 1.5 cosine theta. All right, hell yeah. And how do you know that? Well, this is your angle, the sun is shining, and this is the sine part. This is the cosine part. This is your hypotenuse. It is the bigger number. So these numbers are smaller. You take that bigger number and you multiply it by a smaller number. And the smaller number is sine and cosine. Sines and cosines are numbers between 0 to 1. Always fractions of that whole hypotenuse. That's a good way to remember that. Okay, so now what? So we have our velocity across 1.5 cosine 45. So now we only have 0.79 meters per second going across, and we have that 80 meters. So we have our velocity, and we have our meters. What the hell do we do? Okay, we do 80 divided by our velocity going across. And so here's our new time. I'm going to store that as alpha s. So our new time is alpha s for theta is 45 degrees, and it's it's 101 it's 101.5 seconds. Holy, so that wasn't very good. You know what I mean? Well, we're going to be in the water for 101 seconds. We're going to be in the water longer, but that's not what it says. It says choose the angle to minimize the distance that we're getting carried downstream. Okay, so now how do we figure this out? Well, we need to, so we're going to be in the water for 101 seconds, but we do have some upstream velocity. So our velocity upstream is 1.5 sine 45. You know what I mean? That's like that 0.79 meters per second, and then that's going to be a velocity upstream. Our downstream is 2.5. You know what I mean? So the actual velocity that we're floating downstream, if we could swim 2.5 meters per second upstream, we could just swim in place, but we can't. And in this case, we're still floating downstream. We are going that way. We already figured that one. But we go 2.5 minus that velocity, 1.5 sine 45. It's a 45 degree angle, so it's the same one that we just came up with. So here's our new velocity of floating downstream. And so, okay, so now we have that new velocity and we have our time s. What do? We just multiply that. So I'm going to multiply it by s. And so now we're downstream 173.8 meters. You know what I mean? So that seemed hella worse. So now, you know what I mean? Let's just do like theta is equal to 15 degrees. So we're going to do that, and we're going to get a cosine of 1.5 cosine of 15. Oh, hell no. I've been in radians the whole time. Holy hell. So I apologize. All this crap is totally wrong. Well, just the 45, you know what I mean? The 0 degree angle, but I knew something was up with the 45. We should be getting a better number. That's what I thought. That was red flags there. So, okay, let's do this again. 1.5 cosine of 45. Okay, yes, yeah, and so sine and cosine of 45 is like 70%, 70.7%, because sine and cosine of 45 is 0.707, just think 007. All right, it's a good one to memorize. Okay, so now we have that velocity of 1.06, we have meters, so we got to take that 80 divided by that. We're just playing around, you know what I mean? So now we have a time, obviously s is 75.4, stored as alpha s. And so now we need this component. It's going to be the same. So what do? We take the velocity times alpha s. Hey, we get a distance of 80. Hey, that was pretty good. You know what I mean? So now let's see if we can reduce the angle to 40 and see if that improves it. You know what I mean? So we're going to do that. So we're going to go 1.5 cosine 40. This is going to give me my velocity going across. We do 80 divided by that, and we get that as our time. You know what I mean? So we get a time. I'm going to store that as alpha r, and we get a time of 69.6. And then so we take that time. Oh, bummer. All right, hell yeah. So if we know that time in seconds, and then we multiply by meters per second, then we get the distance downstream. So, but what at 40 degrees, what is our upstream? It's 1.5 sine 40. So we're swimming upstream 0.96 meters per second. We got to go 2.5 minus that. And I don't even know if I did the 45 degree one right. But yeah, you have to get the difference. So now we have 1.5. Now we're floating downstream 1.53 meters per second. And then we multiply that by the time it takes us to get across. In this case, that's alpha r. And we get a distance of 106.9 meters. I think this 80 was crap because we had to go 1.5 sine 45. Okay, that's 1 meter. And then 2.5 minus that. So now our downstream velocity is 1.4. And then we're going to multiply by alpha s. Yeah. So this one should have been 108.56, and then we reduced our angle, and we got 106.9. So So now let's, you know, and you really, yeah, holy, so we reduced our angle and we're getting a better answer. You're like, holy hell, you know what I mean? So now 45 degrees wasn't the right answer, you know what I mean? So we're somewhere near an angle of 40, you know what I mean? So then we can go like, let's go 38, you know what I mean? Theta is equal to 38. So if we do that, we got 1.5 cosine of 38. This is going to be our velocity going across. 80 divided by that is our time. We're going to store that as alpha q. And that's 67.7 seconds. So now we're going to find our velocity swimming upstream. That's 1.5 sine 38. And then we're going to 2.5 minus that. So this is the actual velocity downstream multiplied by the time, alpha q. And we get our distance of 106.69. All right, hell yeah. So we're getting even better, you know what I mean? And so so now here's one, because like this doesn't require any knowledge of how even the equations work. We're essentially just kind of using the units as the equation. We definitely need to figure out a little trigonometry, like the actual velocities this way and then the velocities that way. So now let's actually get an equation, because what were we doing to get distance? Distance was going to be equal to, hey, that time, let's say this q, times what? Times the velocity, which was 2.5 minus the 1.5 sine theta. Okay, so that was distance. We had to get the velocity downstream minus the velocity upstream to get kind of how we float downstream, like the relative velocity downstream, multiplied by the time it takes to actually get across. That's our distance. And then how do we figure out the time q to get across? Well, we said that's going to be this this component. That's going to be 1.5. Well, I mean, we are going to get 1.5 cosine theta, and that's going to give us our velocity. But then we have to go 80 divided by that to get our time. Cool. So this time component is going to be 80 divided by 1.5 cosine theta. And then this part is 2.5 minus 1.5 sine theta. Okay, hell yeah. So this is equation for distance. You know, so after all, so that like when I got this problem, I just had my calculator and I was just like, oh, and I just started doing that. And I actually threw in 45 and that was, and then I threw in like 40. I actually did 44 and then 46. You know, and then realized that 44 was better. And I was like, no way. You know what I mean? I thought it was going to be 45 was the max. Okay, so now that we have this, we can type this into our calculator, because here's another way to do it. We can go 80 divided by 1.5 divided by cosine x, and then multiplied by 2.5 minus 1.5 sine x. And now we can say, hey, 45 stored as x, and then just bring up that equation. And then we get this. And then we can go 38 stored as x. And then bring up that equation. We get this. And we can go 37 stored as x. Do we get better? You know what I mean? Hell yeah, we get better. So then we're going to go 36 stored as x. Do we get better? Nope, we don't get better. It starts to go up. So now we can go to 37.1, you know what I mean, stored as x. Do we get better? I don't know. 37 stored as x. So no, 37 is better. How about 36.9 stored as x? Is that better? Wait, 36.9 stored as x. Yeah, that's better. So 36.8 stored as x. Is that better? No, it's not better. So we're at 36.81 stored as x. Is that better than 36.80 stored as x? It was. So we got 36.8 3 stored as x. You can just keep doing this if you wanted to, so that is a little bit better. Okay, so we're shooting for an angle of 36.8 degrees, and we might just be fine. We found the answer. That's the degrees that's going to minimize d. But now what we want to do is from like, okay, so now the other way to do it is just throw it into your calculator. So now we have 80 divided by 1.5 divided by cosine x, and then multiplied by 2.5 minus 1.5 sine x. And then we can graph this. This is going to give us a y of like 100 to 120. So we need to go window for our y. We need to go, negative 10 to about 120. And then for our theta, we're going to go 0. I guess we can do negative 10 to 90. And then we're going to graph that. So there we go. There's the distance, and I guess we're going to throw a minimum on the y to 100, and we can go up to max of 200, and then graph that. So here we go. So here's our angle. So angle, if we have an angle of 0, so now we can just go a value of 0. If we have an angle of 0, we're going to get that 133. Okay, so we have a check mark on reality there. And then, you know what I mean, we're going to throw a value of 44. Hell yeah. So we're on that side. So look at this. If we do a value of 30, so let's go back to 0, 10 degrees. So if we just have a 10 degree up, this helps, you know what I mean? And then if we have like a negative 5, well, that doesn't help at all. So that would be going this way. If we're going this way, hell no. It just gets worse and worse. You know what I mean? And obviously, if you were swimming downstream this way, you would have very little velocity going across, and you would just spending all your time going down. And if you had a 90 degree, if you had an angle of negative 90, well, you wouldn't be able to put that in your calculator. This thing at negative 90, and we can show that, you know what I mean? So we can go the X-Men negative 90, and we can really just do this like 10 to the 6 and graph it, and we know that it'll do well, what the hell? I guess it didn't. So well, let's get rid of some of these, graph it. But there you go. So yeah, we're showing that it blows up at negative 90. The other time it blows up is if you get to 90 degrees this way. So now we can just maybe throw an extra 0 in here and then graph it. Yeah, so that's how it's blowing up right on the sides. It just shows it blowing up, but it doesn't do a very good job. But yeah, it's always good to do it. Anytime you have an equation, throw it in to your graph, because you should be able to get an idea of what's going on. So now let's go back to 120 or 200, and we're going to go negative 10 to 90. All right, so now we have our equation, and we do have a minimum. You know what I mean? So if we're tracing this out, there's some point where, it's the good. And so like right there at 36.96. Okay, hell yeah. But on a graphing calculator, you do have a minimum. You know what I mean? So you can do left bound, right bound, and then find the minimum. And so this says we have the theta that you wanted, the angle that you want to swim is 36.8698, whatever. So if we rounded it, we'd do 36.9 degrees. So there you go. 36.9 is the angle, basically, and this is approximately 35 degrees. So that's fascinating. And so let's see, before we move on to this, let's see if our swim velocity is 2.5, and if we do our swim velocity of 2.5, does that mean it's going to be at a 45 degree angle? I'm so curious, because why is it messing up? Why didn't it like that? Let's just go 2.0, and then we'll go 2 minus 2.0. Oh, weird. So we can go zoom out. Oh, yeah. No, duh. Because if you could swim at 2.5 meters per second, you technically could go at a 1 degree angle. It would take you hella forever to get across, but you could get across and hit there. So yes, there does have to be a velocity difference. So if this was 2, then our minimum is going to be at 53 degrees. So that is wild, you know what I mean? So if you, this is good for kayaking, because I'm going to tell my instructor, or kind of my old boss, be like, hell yeah. So if you can match the river, you know what I mean? So let's try to do this. Let's go 2.4, 2.5, 2.4. So there we go. We're going to graph that and see what the minimum angle is. See, it's really sharp, so we do get a a definite. So yeah, about 73 degrees. So there you go. If you can basically match the river speed, you still want to minimize your time crossing. And I don't know if it minimizes your time crossing. This just minimizes your distance that you're going to go downstream. So if you can't paddle upstream, but you can get pretty damn close, you do want a hella steeper angle. You know what I mean? If you're just trying to get across. I've been in that scenario. It's like a class 1 river, and I'm trying to get my raft across. You know, so I'm just going to do a hella steep angle. It's gonna take me a lot longer, but I'm not gonna lose very much ground. So this is a very specific question. Is just like, you know, how you know, trying not to lose ground. Okay, and let's do the other extreme. We're gonna go to like a 0.5, and so we're gonna go 0.5, and then we'll see what the other extreme. So if you can hardly paddle with the river, I don't even know why it didn't show up though. So we have, how about let's just do 1, and then graph that. Oh, it's because we're just not even in range. So yeah, if we have hardly any speed, we're just going to be hella down there anyway. But our minimum, you know, let's see what our angle should be. You know what I mean? Our angle should just approach 0, so that makes sense. So yeah, if you're like at half speed or less, you really just want hardly any angle to get across, especially if you're slow. So there you go. And it would just make sense if you were hella slow, you know what I mean? This angle will approach 0. So yeah, there you go. And I mean, that was two fairly extreme cases where your velocity is less than half the river speed. You got to be about a 20-degree angle. But if your velocity can match the river speed, you know, about that 75-degree angle, 70-degree angle. All right, so now let's do this problem for real with this 1.5. So I'm going to bring that back up. And we're going to use differential equations. And what the hell does a differential equation mean? You know what I mean? Because we have a minimum, so the slope right there is 0. And I just want to know. I just want to trace this out just to make sure we're got the same problem going. Yep. And so we have a minimum slope there. So if we go take the derivative of our function with respect to theta. Now what does this mean? You know what I mean? And this is our distance function. It could also be y or whatever. So we'll have like dy d theta, derivative of our function. So this says if we change our function just a little bit, it basically says if you change the angle just a little bit, you're going to have some change in this function. You know what I mean? You're basically going to have some change in the distance. So this also is d, and I'll do capital D here. So we have d theta. So if we change our angle just a little bit, our distance is going to change. Now if we choose to do like for our problem, if we choose to do like a too steep of an angle, well, guess what? If we're like at a 70 degree angle, we get a distance of 107. We're way the hell down there, 172. And so now let's increase our angle to 73. And then we go from 172 to almost 200. You know what I mean? So we go 30 meters. So now let's go back to our ideal angle of like, so let's go to 40. So if we're at 40 degrees, we're going to be like at 106. And now let's go to 43. Now we're just at 107. So you see how that we increased our angle by 3 degrees, and in one case we went 30 meters. So that's the slope of that line, and it shows you your change in your distance compared to your change in your angle. The other time we went 3 degrees, and we only went like 1 meter. You know what I mean? So so there you go, and it's at the location where your change in your distance, d theta, if that's 0, then you're at a minimum or you're at a maximum. You know what I mean? And in our case, our problem just works out that when that's 0, we hit the minimum. Okay, so now what we're going to do is use our differentiation skills and do this thing. So we're just going to call it y. And we're going to go 80 divided by 1.5 cosine theta, 2.5 minus 1.5 sine theta. I mean, we answered the problem, but right now we just wanna do dy d theta like a pro. You know what I mean? So what should we do here? Should we FOIL this through? I think we should. So we're going to go 80, 2.5 divided by 1.5. And then we got cosine theta downstairs. Okay, hell yeah. And now we're going to go minus 80, 1.5. We got sine theta upstairs. And then we got 1.5 cosine theta downstairs. Okay, and so we're just going to leave it like that because I got differentiation skills. I just learned these tricks. You know what I mean? The trick is if you have like something upstairs, downstairs, like obviously this, you use this thing. You use d u uv. So d like the derivative of uv dx is so here's this. It's the second times the derivative of the first minus the first times the derivative of the second, all divided by v squared. You know what I mean? So I don't have my book with me, but we kind of memorized some of these. Okay, and we can use the same strategy for this. This is just 1 upstairs, so we're going to say, hey, in this case, factoring out a constant, so let's do it. So what's our v right here? Well, it's going to be 1.5 cosine theta. What's our du? So this is our u, and if we take the derivative of a constant, it's just 0. Okay, so hell yeah, that just goes to 0. Now we're going to minus, so we have our u, that's 80, 2.5, and then we have our dv dx. So now we have our derivative of this. So now we need to know what the derivative of sine and cosine are. So sine starts out at a 45, basically goes like that. And so what the hell is the slope of this? It's the slope of 1. Look at it, you know what I mean? And so now the question, if this is sine x, the question you want to ask yourself is like, hey, if this needs to be 1, what equation, when you throw in an angle of 0, is 1? And well, that's cosine. Cosine of 0 is 1. So hell yeah, the derivative of sine x is cosine x. Now for cosine, it's a little different. Cosine starts at 1 and then goes this way. Well, hey, look at that. The slope at angle of 0, look at that. The slope is 0 right there. So what equation, when you throw in 0, is 0? Well, hell yeah, sine x. But you just have to remember that, hey, look at how cosine curves down. So it's a negative slope. So if this is cosine x, the derivative is negative sine x. All right, hell yeah. So now what we got here? So now we're doing this. We got u, and we're taking the derivative of 1.5 cosine. Well, it's going to be negative sine x. So we got negative 1.5 sine x. Cool, we're on a roll. And then we just all divide this by v squared. And what's our v? Well, it's 1. So we got 1.5 squared, and then cosine squared theta. All right, hell yeah. So moving on. So we got that term done. Okay, now we're going to move to this term. Same thing, we have a u and a v. What do we start with? We start with v. So we go 1.5 cosine theta. Now we need to take the derivative of the u. Well, this is sine, well, let's ignore this minus sign. But this is sine x, sine theta. So the derivative is cosine. Now we'll obey that negative. So we have negative. And this is just multiplied. So we got negative 80 1.5 cosine. What the hell? So we did our v, 1.5 cosine theta, and then we said, no, I think we're on the right track. And then the derivative of this top part, that's going to be sine x. Yeah, the derivative of sine x is cosine. Got it. It's only cosine where the derivative is negative sine x. Cool, so we got cosine theta, and we're all good in the hood. And then so now we're going to minus the u part. Ooh, we're going to run out of room, but 1.5 sine theta, that's the u part. What's the dv part? Derivative of cosine, that's negative sine. We already talked about that. So we got negative 1.5 sine theta. Cool, hell yeah, just ran out of room, but we're done over there. And then divide by 1.5 squared cosine squared theta. All right, hell yeah. So both these are divided by 1.5 squared sine theta. Let's see if we can simplify anything. So this is going to be a positive 80 2.5 1.5 sine x. This is going to be now we got to be careful here. I think you need to foil through the negatives first, because this is like all negative. Like once you take this, then you subtract it. But so yeah, you got to treat this as a whole thing. And so over here, these become positive. I get that. And so we could factor through this negative. So we could go plus, but then we got to go plus here and then minus all this stuff again. Yeah, I'm okay with that. So now this is going to be a cosine squared. So we're going to have 80 1.5 squared cosine squared theta. And now this, we're going to have a sine squared and another cosine squared. So now we're going to have minus 80 1.5 squared sine squared theta. Now, if this was like additive, which it wasn't, we already saw that it wasn't additive. There is a negative between these. The sine squared theta and cosine squared theta would go to 1, but it's not that. So, and I'm sure there's other identities in the book, but you know what I mean. It's like, who cares? And we got our equation. So now let's write it. dy d theta. And, I'm sure there's probably hella errors, but let's write it one more time. So now we can just put this stuff also on top. So we're going to go add to 80 1.5 squared cosine squared theta minus 80 1.5 squared sine squared theta. Okay, hell yeah. And then divide by 1.5 squared cosine squared theta. Now there's not a 1.5 squared over here. And then should I double check this? Like why didn't this stuff well, it's because we had a sine and cosine. Over here we just had the cosine component. Okay, so let's type this into our calculator, and what we would expect is that the 0, if we set this equal to 0, our theta would be that 36.9. So that would be a check on reality. All right, so, and I'm going to cross out this one, so I'm going to go 80 times 2, 80 times 2.5 times 1.5 sine x. I guess I have to have a parentheses right at the beginning. Now we're going to go plus 80 times 1.5 squared cosine x squared minus 80 times 1.5 squared sine x squared. Okay, parentheses divided by 1.5 squared divided by cosine x squared. Okay, hell yeah. And now we're just going to graph this. And, you know, our window should be 0 to, so in our x, now we're going to have like 0 to 90, you know what I mean, for our angles. And now we can just, for our change, I don't know what we need, you know what I mean. So let's just do negative 50 to 50. Yeah, but we probably did something wrong. That's the bummer of this, you know what I mean. Yeah, so that didn't work at all. So yeah, so we have an error, and I don't want to bore you, but I want to do this differentiation. I find it fun and fascinating. So I'm going to go through and find any errors and catch on the flip side. All right, hell yeah. So we actually took this to Wolfram Alpha. Now I don't have a printout because it actually didn't make a graph, but it did give me this equation. So this top equation, I at least put it in, and that gave me kind of a starting point. And then I went back and kind of cleaned it up again, did the same process, and yeah, we kind of just lucked out. So this next one we threw in, and then we decided to make it just a little bit easier, because if you look at this, we have one is just this divided by cosine, but then this is sine divided by cosine, and that's tangent. You know what I mean? So, man, this book is great. Eschbach and Handbook of Engineering Fundamentals. I really enjoy the differential section. It's just such a nice printout. And so, heck yeah. So you have tangent, deriving tangent becomes secant squared, which is just 1 over cosine squared. So we come over here, tangent secant squared, 1 over cosine squared, and we just have a theta in there, and then everything else is a constant. Oh, and the other thing that we did is we saw that 1.5s cancel. So this thing just really becomes 80 tangents. We just need to find the derivative of that. So this first part was the same, you know what I mean? You use the same method that I used. And then the second part is just 80 divided by, and then even this though, I mean, 1 over cosine is just a secant. So we could have done this. Is this says tangent, secant u, tangent u. So we could have used that, but we did it our fancy way, and it still works out. But I did want to use the book to make this into tangent. I take the derivative of the tangent, which is 1 divided by cosine squared, so we did that. And then we throw that in. So in our calculator we also have that one, and then we have yeah, so we have that. And then I was just like, well, can we multiply by a sine on both of these? You know what I mean? And turn this into tangent squared divided by sine, and then sine divided by sine to turn this into tangent divided by cosine. And the last graph, it didn't work out. So now my question is like, hey, if I have tangent divided by cosine, can't I just multiply by sine on both sides and get tangent squared divided by sine squared? Are those the same two graphs? I haven't freed up my calculator to figure that out. But we're going to end with just having these graph out. And I should have been having that going while we're doing it. But at least you can see, this is in radians. And I think we have 2 pi radians, so halfway is 180, a quarter is 90, and then so we for sure, and it's really slow graph. I might actually, we got 3 more of these maybe. But then you have the angle where it crosses, which is right at that right at that 40-degree mark. So that was the whole thing. We wanted to have an equation that crossed the x-axis. And then that last one is just a little bit off. You know, that was the only one that was a little bit off. But now we can go in and get our 0 value, and we're just going to get a guess, 0.9? There you go. And get our 0, we're going to do left bound and then right bound. And we can really use any of those equations except that last one. Whoa. You know what I mean? Do we have an error here? I don't know. So left bound, right bound. Yeah, so maybe this isn't the equation, because we have an x is equal to 0.64 radians. So now let's go that x times 360 divided by 2 divided by pi. Yeah, no, that's 36.87. You know, 36.9. And I took such a big break from this problem, but hell yeah, that's the angle that we were finding. But yeah, and in radians, it is just. I'm getting confused between problems. You know what I mean? That was the deal. I'm getting confused between a couple different problems right now. One that I did, but yeah. So the radians on this was 0.64 radians. This is just the first time that I've actually seen that in radians. That was the only confusion. I've just been doing too many problems today. So anyway, so hell yeah. So we did that's what I wanted to do. I want to do more using the formulas for derivatives. Because actually, it's pretty simple. I hear that integration is way complex, but you know what I mean. Differentiation has very classic rules. Even if you get some long-looking equations, hey, they still work. So anyway, I'm going to end it there, and thanks for joining me.